All right, subscribers, welcome back to another episode of Science with Surback. Today, what we are going to be talking about is AP Chemistry Section 17.3, and this deals totally with titrations. Now, a couple of objectives I want you to be able to meet by the end of this lesson. Objective number 1, describe the form of titration curves for the titrations of a strong acid by a strong base, a weak acid by a strong base, or a strong acid by a weak base. Objective number 2, calculate the pH at any point, including the equivalence point in acid-base titrations. So what we first get started with is, what is titrations? And titrations just happen when a solution of base of known concentration is added to an acid, or an acid known concentration is added to a base. So real simply put, a titration is adding a base to an acid, or vice versa, adding that base to an acid, or what we have down here. Now, the big thing here with us, we've been looking at the pH of what happens as we make adjustments, as we added in the last section a common ion, and we're focused on what is that pH. Ultimately, what is that account, or what does that log of hydronium ions look like? Now, what we can do with titrations, they actually form these nice curves, and we're going to talk about this in detail at the end of this section. But pH titration curves are going to have two main components. Number one, that first component is they are going to show a plot of pH versus volume during a titration. Alright, so what this plot means is that we have a graph, and I'm just going to put a generic graph here, and I'm going to have my X and Y axis, and over here I am going to add my pH on the Y axis. So this is the pH of whatever solution. And then over here, this is the amount of volume, added. Now, a generic titration curve. This, I'm just going to show you, is a strong acid titrated by a strong base. But what you would get is a strong acid, and then at what we call the equivalence point, you'd see this dramatic change in pH. And now the pH here, we would have this dot, and this dot is known as the equivalence point. So that's the other thing that a titration curve shows. And we'll talk more in depth about an equivalence point, and it'll make a little bit more sense as we add some acid to a base and we go through a titration. But right here, the number of moles, and I'm going to use some abbreviation, the hashtag symbol here, number of moles acid equals number of moles of our base. So that's something to keep in mind. At the equivalence point, the number of moles of the acid is equal to the number of moles of our base. Now, this point right here, I'm going to do some abbreviation, but that dot right there is our equivalence point. And a little fast forward sneak peek, a titration of a strong base with a strong acid, or vice versa, is going to have an equivalence point equal to 7. You're going to have a completely neutral solution at the equivalence point of this particular scenario here. Now, we have 3 different types of titrations, and really we can have a little bit more than that. But the 3 types of titration is a strong acid, strong base titration. The second type of titration is a weak acid with a strong base. And then the third type of titration is a polyprotic acid with a strong base. And remember that a polyprotic acid is an acid that can actually have more than one ionizable H plus or proton. Now, we actually can have a couple more types. We could have a strong base titrated by a strong acid. We could have a weak base titrated by a strong acid with that too. So we actually will have 5 different types. We just classified these as 3 because they're going to follow some general trends. But we can have more if we throw in that business of weak bases and strong bases. So keep that in the back of your mind. Even though I went over 3, there can be a little bit more added. Now, the best way to go over this is jump right into the fire here and start out here with a particular problem. So we want to know what is the pH during a strong acid, strong base titration. So right here in the first problem here, we add 49 milliliters of 0.1 molar NaOH solution to 50 milliliters of 0.1 molar HCl solution. So again, the very key thing is write out our equation that we are dealing with. So we are dealing with a strong acid. That's initially what we have in our beaker or our flask that we're doing this particular experiment to. And in this, our hydrochloric acid, HCl, is going to be an aqueous solution. That means it got dissolved with water. And this is unique. Remember, HCl is a strong acid. So that means there is no equilibrium here. There is one reaction arrow, and we produce our hydronium ions, and we produce our chloride ions. Now, what happens here, and the problem doesn't ask for this, but what happens here is we have 0.1 molar HCl. Now, initial pH, before we even add any of the base, our initial pH is just negative log of our concentration of our acid, which is the concentration of our H3O plus. Again, because it's a strong acid, all of this 0.1 molar gets converted to 0.1 molar of our hydronium, our H3O plus concentration. So our initial pH is this. It is just equal to the negative log of 0.1 molar, because that's how we find our pH. And so if we take the negative log, of our initial pH, which is 0.1, we get a pH, I don't know if you saw that, we get a pH of 1. That's our initial pH before we even add any particular base. Now, what happens here? We add sodium hydroxide. So this is what we were talking at the end of section 17.2. What happens with sodium hydroxide is this. Sodium hydroxide, it's an aqueous solution, and it breaks down to sodium ions, and it breaks down to it breaks down to OH minus ions. Now, what we have to think about is this. We had 49 milliliters of 0.1 molar NaOH added to this solution. So what this means is we're going to have to do a little bit of math here. Now, initially we had 0.1 molar HCl. However, we only had 50 milliliters. So we're going to concentrate on this. We're going to say we need to find the number of moles of HCl. So that should be step one here, is we should find our moles of HCl. So our moles of HCl is equal to this. We have 50 milliliters, which 50 milliliters, if you divide that by 1,000, and I'll show you that on my calculator, 50 milliliters divided by 1,000 equals 0.05 liters. And this is important coming up here, 0.05 liters. We need to start out with what we have, because we have 0.05 liters of HCl, and we have to multiply this by our molarity. Now our molarity is 0.1 molar. What that means is that there is 0.1 moles of HCl per every liter. And now if we do this equation right, we take 0.05 times our molarity, which is 0.1, and we get a value of 0.005 moles of HCl. All right, so now we have to think about this NaOH. When we add NaOH, we are directly affecting, we're taking this hydronium ion concentration and we're reacting with it, and so we're reducing the amount of HCl or H plus from the hydrochloric acid that is ionized. So what we have to do here is we have to find out our moles of really hydroxide, or NaOH we can say. But what we do here, we have 49 milliliters, which this out here, I'm just going to make a little side note, this out here is 0.049 liters. All right, so we got to do a very similar thing to calculate the number of moles of OH minus added to this particular scenario. So we start out here with 0.049 liters times our molarity, which lucky for us, we have 0.1 molar, which means for every liter of solution, we have 0.1 moles of NaOH. So because we're dealing with NaOH, we get, if we plug this into our calculator, 0.049 times our molarity, which is 0.1, gives us 0.0049 moles of that OH minus. Now, this is important to listen, because as we add our moles of NaOH, it takes away our moles of HCl. So what happens here is that for every mole of NaOH we add in this circumstance, we take away a mole of HCl. So right here, this is set up real nice because we can just perform this subtraction, and what we end up getting is this. If I take 0.005 minus 0.0049, I get a value, number of moles of HCl that is left. This right here is 0.0001 moles of HCl that is left. Okay, because every mole of NaOH that we have, which we calculated, we had this amount. Every mole that we add, we have to take away our moles of HCl. So right now, after we add 49 milliliters of this NaOH, we are left with 0.0001 moles of HCl. Now, I'm running out of paper here, so what I'm going to do is I'm going to grab just a blank sheet of paper. And out to the side here, we have to do some thinking. So our pH of a strong acid is just equivalent to the molarity, keyword molarity, of our strong acid. So what I'm going to do is I'm going to take our 0.000 moles of HCl that is left. And then the equation for molarity is moles of whatever substance you have divided by liters. We have to do some thinking on this. We started out with 50 milliliters of this solution, and we added 49 milliliters. So the number of milliliters that we added, we had 50 and we added 49 milliliters. So right now we have 99 milliliters of solution. Now our molarity formula tells us we can't just have milliliters, we have to have liters. So what I'm going to do is I'm going to divide this by 1,000, and this gives us our number of liters total in solution. And I'm going to actually write that down. So this is 0.099 liters of solution. This is total solution after we've added everything together. So what I need to do is this. I need to take 0.0001 moles of HCl, and I need to divide it by my volume in liters, which is 0.099 liters, and I'm going to press enter. Now, on this, what I get is a molarity of 0.001. So that becomes our molarity of our HCl after we have added our strong base to our solution. So now that we have this in molarity, we can find the pH of this solution, which is just for a strong acid, is just the negative log of our H3O plus concentration, which is equivalent to our molarity of our strong acid. So in this case here, our pH equals our negative log of the hydronium molarity, which is what we just calculated. So it's 0.001 moles here. So when we calculate this out for this first problem, all we're going to do here is take the negative log of our pH, which is 0.001, and we press enter, and we get a pH of 3. Now, a pH of 3 is still acidic. However, it is a little bit higher than that initial pH of 1. Okay, so what we're going to do now is we are going to add in problem number 2 here, right below, we are going to add 51 milliliters of this NaOH to, again, our 50 milliliters of 0.1 molar HCl. All right, so I'm going to make some notes here, and it's going to use a lot of information here from above in problem 1. So again, I always like to get a game plan, get a roadmap of where we're going here. We have HCl, which is in solution. It's dissolved in that water, and remember, it's a strong acid. So we have just one reaction arrow going left to right, and so we form H3O plus, and we have Cl minus. Now, from what we calculated up above, we started out here with our 0.1 molar, which was helpful, but originally we start out with more importantly, with 0.005 moles of HCl. So I'm going to put down here and this 0.1 molar, really importantly, is 0.0 HCl. Now what we've done is we've added 51 milliliters of NaOH. And now, looking at this at first glance, it may not seem like a big deal or a so what, but what I want to do first is this, and I probably should have done the other problem like this. I want to calculate the number of moles of NaOH. And so we do this. We start out with the amount of liters, which if you take 51 divided by 1,000, what you'll end up getting is 0.051 liters of solution. So we get 0.051 liters of NaOH, and we're going to multiply it by its molarity. Now again, lucky for us, we still have that 0.1 molar. So that means for every 1 liter of solution, there is 0.1 moles of NaOH. All right. Now, we perform this calculation, and we get this. We get 0.051 times 0.1, and we get a number of moles of 0.0051 moles. Okay, so this is important, and maybe some of you can see this. So this is 0.0051 moles of NaOH. Now what has happened is this. We've had the tides turn. If you look closely, this number, 0.0051 moles of NaOH, is bigger than the number of moles of acid that we have. So in this case here, what's going to be left in solution, what we can actually calculate, and I'm going to use this equation, is going to be hydroxide OH minus ions. So we've consumed all of our moles of HCl, and so whenever you have a greater number of base than our acid, what is going to be left in solution is going to be just your strong base, your OH minus ions. So what we have to do, we have to figure out, well, how much sodium hydroxide, in particular, how much or hydroxide ions is left in our solution. So what we have to do, this is really an important step. We have to take 0.0051 moles of NaOH. And remember, this stuff reacted with 0.005 moles of HCl. So for every 1 mole of strong acid or base we add, we have to take that strong acid or base away in terms of moles. So what we do, we subtract out our number of moles of our acid that we use. So what is left over when we do this is, and I can perform the calculation here, we had 0.0051 moles. We utilized 0.005 moles, or we reacted with that, and we're left with 0.0001 moles of NaOH. Now, just like we did on that other sheet of paper, I ran out of room up top here. To calculate in this case, the pOH, I cannot have I cannot have our moles. I can't just plug this into our calculation. I have to put it back into molarity. So we have to divide it by our total liters of solution. And we got to do some thinking on this. We added 51 milliliters to something that already had 50 milliliters. So what I'm going to do, I'm just going to add together those two numbers, 51 plus 50, and we obtain a value of 101 milliliters. Now the definition of molarity is moles divided by liters. So what I'm going to do is I'm going to divide that number by 1,000, and this becomes our total liters of solution that we need. So we have this 0.001 moles divided by 0.101 liters of total solution. So what we end up getting is this. We take 0.0001 divided by 0.101, and we obtain this. We obtain 0.00099 molar NaOH. So we get 0.00099 molar of NaOH. Now, the definition of a strong base, we can utilize the molarity to find not our pH, but our POH. So what we can do is our POH is equal to the negative log of our hydroxide concentration, which is equivalent to our NaOH. So what I'm going to do is I'm going to plug this value into our POH equation. And so we get 0.00099 to be inserted into our equation. And when we do this, we get a pH, negative log of 0.00099, close the parenthesis, we get a POH of 3.00. Now, again, this is our POH. The problem, if we look at it here, it said, what is the pH? So remember, from our KW equation, 14 equals pH, which we don't know, plus our POH, which is 3. So to get pH isolated by itself, we subtract 3 by each side. And so this allows us to find the pH of this solution to be exactly a pH of 11.0. Now, think about this in terms of what just happened. We added just 2 more milliliters of this sodium hydroxide solution, and we went from a pH on our other sheet of paper. We calculated the pH to be 3 on problem 1, which is an acidic solution, and then we added just 2 more milliliters. And now all of a sudden our pH is 11, a dramatic difference. So with a strong acid, strong base titration, adding a little amount when we get really close to equivalence point or right at it or just past it is going to make a significant difference when we go to calculate our pH, or when we find our pH. Now, this was one half of the problem. Now what we can do, and some people may like this better, is we can look at what happens when we have a weak acid titrated by a base. So we'll change out our papers here. Alright, so now as we go to this next problem here, we are going to calculate, like I said, the pH of a weak acid that is titrated by a strong base. And I know what you may be thinking. We've done weak acid and weak base problems, and they are quite time consuming.
However, luckily for us, what we have, we utilized the Henderson-Hasselbalch equation in the last section, and we're going to be able to use that. So actually that becomes into our benefit for this problem, and I'm going to show you how we can do this. So in this problem, it wants us to calculate the pH of a solution when we have 45 milliliters of 0.1 molar NaOH titrate a 50 milliliter solution of 0.1 molar acetic acid. Now, what I like to do, again, I always like to show a roadmap of where we're going. So initially what we have this acetic acid. So we have CH3COOH, and it is placed in water, H2O, and it forms equilibrium because it's a weak acid. It forms that H3O plus and that acetate ion. Now, what happens here is this. We have to think about what we initially have. And so we initially have this 0.1 molar acetic acid, which, as you saw in the last problem, wasn't as helpful. So instead of having 0.1 molar, I want to know how many moles of this acid that I have. So out to the side here, I have 50 milliliters, which, just as a reminder, 50 milliliters is equal to 0.05 liters. And so what I do to calculate the moles of acetic acid, and I'm just going to put moles of acid, I take my 0.05 liters and I multiply it by my molarity. And so the molarity of my weak acid is this. I have 0.1 moles of our acid for every 1 liter. So in solution here, what I have is this. I have 0.05 times 0.1 to give us 0.005 moles of acid. Now, this is a lot more helpful. I'm going to write this down below here. We have 0.005 moles of this acetic acid. Now, we added 45 milliliters of our 0.1 molar NaOH. So what we have to think about is this. For every mole of strong base that we add, it reacts with our acid and it helps neutralize the solution. So what happens here is this. Right now, we don't have any acetate, these ions, in solution, and we need that to be able to calculate our or utilize that Henderson-Hasselbalch equation. So what happens here is this, that for every mole of strong base we add, we have to take away our acid and we add in our conjugate base here. That's CH3COO minus. So over here, or down below, I'm just going to put moles of our base, our strong base that is added. And so we've added 45 milliliters, which again, just a side note, 45 milliliters is 0.045 liters. And so we have 0.045 liters times our molarity, which again is just 0.1. And so we have in solution, when we added this, we actually have 0.045 times 0.1 to give us 0.0045 moles of acid. Now, what happens here, and it's really important to pay attention to this. For every 1 mole of base that we add, we have to take away a mole of acid. So what happens is this. We are left with 0.0045 moles, or we take away that many moles of our acid. And so when we perform this calculation, our acid that we add, so we take 0.005 minus 0.0045, and we end up with 0.0005 moles of acid that is left. Now, we have to think about this. For every mole of that strong base that we add, we shift the equilibrium even further to the right, which means we produce more of this acetate ion. So here, because we added 0.0045 moles of our strong base, we shift the equilibrium over to the right, and we add 0.0045 moles of our weak or our conjugate base here. So now we have this, and I'm going to write this down. I'm just going to copy and paste this, 0.0045 moles of our base. Now, before, in this Henderson-Hasselbalch equation, I would have you find the molarity. Remember, we had to put it back into molarity. But that Henderson-Hasselbalch equation, if you can remember the outline of that formula, the base divided by the acid is just a ratio. And because these two things are in this case, 95 milliliters of total solution, they would both be divided by the same amount of solution. So what we can do for this titration, because we have moles, what we can also do is this. We can utilize the Henderson-Hasselbalch equation, so our pH is equal to our pKa plus our log. In this case, the log can be the number of moles of base divided by the number of moles of acid. So let's go through and let's see if we can't solve this problem now. Our pH, that is what we are after. That is going to be our big question mark. Our pKa, it's not given to us outright, but remember our pKa is our negative log of our Ka, which our Ka was given in this problem to be 1.8 times 10 to the negative fifth. So we take negative log of 1.8 times 10 to the negative fifth, and we obtain a pKa value. Let me plug this into our calculator. Negative log of 1.8 times 10 to the negative fifth, and we press enter, and we get a pKa of 4.74. So 4.74 becomes our pKa, and then our moles of our base. In this case, the number of moles of NaOH added, remember, shifts that equilibrium over to the right. So we can say the number of moles added of NaOH is equal to our number of moles of our base, which would be this acetate ion. And so we can just say, hey, we have 0.0045 moles, and I'm going to add some details, moles of this acetate ion. And that's important to note, or at least have in your mind, because to use this is the conjugate base and that weak acid, not the strong base, even though that gives us that value. And then our moles of our acid. Remember, for each mole of sodium hydroxide, that strong base we add, we have to take away from our original amount, our original value of moles of acid. So our moles of acid, which we calculated here, is 0.0005 moles of, important here, of acetic acid. So CH3COOH. Again, weak acid and its conjugate base. We have to have that to be able to use the Henderson-Hasselbalch equation. And again, to emphasize this, we can use moles in this case because it's a ratio and because we would be dividing by the same amount, that ratio would not adjust or would not change. So to find our pH of this particular problem, we take our pKa, which we said was 4.74, plus the log of the number of moles of our base, which was 0.0045 moles, and we divide it by the number of acid moles left, so 0.0005 moles of our acetic acid. Now, what we do from here is this. We just plug this into our equation, or our calculators, how about? 4.74, that's our pKa, plus the log of our base, which is 0.0045 moles, divided by our moles of acid that is left, which is 0.0005 moles. When we calculate this, our pH becomes 5.69. So, a little bit easier problem, but you have to conceptually think, okay, as I have a weak acid, the only way to get a conjugate base is to add some of that strong base, and that allows us to use the Henderson-Hasselbalch equation. Again, we can use the moles because it's just a ratio, so both of these are in the same solution. They would be divided by the same amount of liters. This allows us to use this Henderson-Hasselbalch equation. Now, we've done a lot of calculation, and I know it's time-consuming here on this front. So what we can actually do is we can shift over just to some thinking about how we can actually calculate and go through titrations in each of actually 5 scenarios. So let me change out the papers here, and let's talk about the last 2 values or last 2 pages of these notes. Okay, so as we get into this, like I said, the titration problems, the calculations are a little bit time consuming. So if we can just conceptually go through the process or go through the steps of how to calculate these particular problems, I think we can do a lot here, a lot of good with these values. So number 1, we're going to go through actually 5 titration curves. And the first one is a strong acid, strong base titration. So very similar to those first problems that we did in this video note. So first off, this is the pH of the solution. And in this case, because we are starting out with a strong acid, our strong base down below here, this is going to be the volume of base that is added. Okay, and that is going to be in milliliters. Now, a strong acid is going to have a very, very low pH, and so our initial values here are going to be very close to the bottom. Now, as you add the base, the strong base, there is a slight increase. There is a slight increase in pH, but not very significant. Now, as you saw when we hit that 49 to 51 milliliters, we saw a sharp increase in pH. So what happens here is this: at that point in a strong acid, strong base titration, you get this dramatic uprising of pH. And now what we get to is this. Our equivalence point right here with this dot, for a strong acid, strong base. And I'm going to put this. EQ is going to be my symbol for equivalence point. For a strong acid and strong base, this is equal to a pH that is 7. Now, going through these particular calculations, we have this to think about. Number one, initial pH, our initial pH is just going to be below 7, number one, because it is an acid. So the pH is going to be less than 7. But to calculate that initial pH, what we are going to do is we are just going to utilize that pH equals our negative log of our concentration of hydronium or H3O plus ions. Now, as we add some base before we get to the equivalence point, so between our initial and before the equivalence point, we get to this second value here. So I'm going to use some abbreviations, but between, I'm just going to abbreviate as B/T, between initial pH and equivalence point. Again, equivalence point, I'm just going to say EQ. Our pH is determined by excess acid. Now, what we have here is this. That excess acid, remember we had to subtract out for every mole of base we added, we subtracted out our acid, and we plugged that amount of acid in molarity, we got to factor that in, we plugged it back into this equation. So the first two things are going to use the same equation, but we have to take out the moles of base added from that moles of initial value of our H+. Now, at the equivalence point, the number of moles of acid equals the number of moles of base, and in that, what you have is just the same equation we did for the autoionization of water. And so this one, for a strong acid, strong base titration, the pH equals 7. Now, if we go past the equivalence points, or after the equivalence point, the pH is determined by the amount of excess strong base. So, in this case here, the pH is amount of excess strong base. And so for this, remember, the formula that you'll actually have to use, because we have strong base, is the POH is equal to the negative log of amount of concentration of hydroxide ions. And then to find the pH, you obviously have to take 14 minus whatever that POH is. So quite a few steps here to go through this. What I want to do, I want to walk through number 2 all together, and then I'm just going to put down what exactly I want for the others, or what to expect, so you have those somewhere in your notes. So we get to a weak acid, strong base titration. We just ended up doing this, and we get this. So a weak acid, remember, it's not going to have as strong of pH or as low as a pH as we initially did up above here. And then another thing is this. So Hopefully you can see the difference here. But our value here, see how this line's a lot steeper? And that's because a weak acid cannot absorb or has more pH affected as that strong base is added to it. And just to remember, this is our pH, and this, because we're adding a volume of our base, we have this. Now, the equivalence point in this case, I'm going to emphasize this. The equivalence point, remember, equivalence point is number of moles of acid and base are equal. Number of moles, acid and base, are equal. The pH at the equivalence point is going to be greater than 7. And that's because, hey, we have equal moles of hydroxide ions to that weak acid, but hydroxide is a strong base. So that's why the pH at the equivalence point is greater than 7. Now, before we add any base, our initial pH is just equal to a weak acid problem. So a weak acid problem, unfortunately, there's no way around it, but you have to use that ice chart. You have to use that ice chart. And it stinks because it's a lengthy type of problem, but we have to do that. Now, our pH is still going to be less than 7. Between initial pH, and equivalence point. Again, equivalence point is just going to be EQ. What we have here, we can utilize the Henderson-Hasselbalch equation like we did in that past example. We just have to remember, for the amount of base that you add, you have to take away the acid, and that amount of base becomes that conjugate base that you use in that equation. So you can use the Henderson-Hasselbalch equation. Now, after I got ahead of myself. After you add or get to the equivalence point, what happens here is this: all of the base has been consumed, or all of the acid has been consumed by all of the acid. And so at the equivalence point, the pH is going to be greater than 7. And we talked about that. Again, strong base titrating a weak acid. And so the pH is going to depend on the conjugate base concentrations. So pH depends on conjugate base concentration. I'm going to put conjugate base concentration there. All right, so then after the equivalence point on number 2 here, we get to this. The pH is going to be just equal to the amount of strong base. So like our top one here, pH equals amount of strong base. And now, okay, so I know I used a lot of paper here, but these 4 steps here are equivalent here to number 2. So what I'm going to do, I'm going to pause the video. I'm going to write out some stuff for our polyprotic acid titration, and then I'm just going to briefly explain about this. All right, so for a polyprotic acid, couple of things. Poly means many ionizable protons. So what that means for us is we're going to have multiple equivalence points, and then in this, for our example here, sulfurous acid is a weak acid number 1, so we're going to have multiple weak acid types of problems where we're going to have to use that ice chart. So it complicates things a little bit more in terms of that. Now, I'm going to provide a summary that's going to be a little bit neater than this what we have in notes, but I do want to talk about weak and strong bases. We really didn't talk about it a whole lot. We didn't do a problem, but a strong base and a weak base can be titrated in a very similar fashion. So what I'm going to do here, I'm going to show you the curves. I'm going to write it down and pause the video, and then go through, well, how do I calculate each particular step? How do I go through each and every fashion there when we make that here? So I'll start out with a strong base, and then I'll move to a weak base. All right, so a couple of things to emphasize here. Again, a strong base, there's not going to be much differential in our pH initially. Then we get this dramatic drop off here. And the equivalence point of a strong base, strong acid titration is equal to 7. And initially the pH, we can find the pOH by taking the negative log of the hydroxide ions with the concentration of that strong base. And then once we add some acid, remember there's going to be an amount of excess base. So again, the amount of excess base goes into that pOH equation. At the equivalence point, the number of moles of acid is equal to the number of moles of base. We get that auto-ionization of water, and so that's how we get a pH of 7. And then after that equivalence point, our amount of excess strong acid is going to be utilized to calculate our pH. So again, I'm going to pause the video here for a weak base, strong acid titration, and then talk about these particular steps down below. Alright, so here is that summary of a weak base strong acid titration. Again, here's the steps. Looks very similar to that weak acid strong base titration. And again, I know this stuff is scrunched and it's squished into place, so I will provide a document that outlines each of these titrations and gives you an idea about what to do with each step. Now, one thing I do want to emphasize here is our pH indicators. So a pH indicator, remember, was that chemical that we placed in an acid or base to indicate what the pH is. In a pH indicator, when you utilize it in this process of a titration, the pH indicator should be able to detect the equivalence point, and we need to use an indicator that changes color somewhere close to the pH at the equivalence point. So an example is a strong base being titrated by a strong acid. It uses the indicator phenolphthalein because it changes color between 8.3 and 10.0 in terms of the pH. Again, there is that written example. This pH range where it changes color goes through that equivalence point, and that's why it is utilized as an indicator in that scenario. Alright, so I owe you a better written out portion of these titration curves. But I hope you've enjoyed this video. I know it's kind of lengthy, but a lot of chemistry got discussed here. If you like this video, don't be afraid to hit that big thumbs up button. And as always, don't forget to subscribe.